Impulse response, step response, and system response. Idea is same that if you have a system represented by h of z, if your input is an impulse, the response of the system is going to be impulse response. So if you have x of n and x of n is an impulse, the system response is going to be impulse response, which will simply be h of z, because x of z, if xn is an impulse, x of z will be 1. If x of n is at a step, then the response of the system will simply be a step response. And x of n step means that x of n is equal to un means, you did that already, that x of z will be equal to z over z minus 1. Right, so you multiply that by h of z and then solve it using inverse Laplace transform. First do the partial fraction of y z over z, and then the inverse response, z transform. And finally, if x of n is any other function instead of impulse or step response, if it is any other function like we saw earlier, you had x of n 0.6 to the power n. In that case, it is simply referred to as y of n will simply be referred to as system response. Okay, so as we did in the last chapter, what is the procedure to find the system response, whether it is impulse response, step response, or simply the system response? First, you're going to convert x of n into x of z, multiply that to h of z, and then whatever polynomial you will have, you're going to multiply that polynomial both sides by z to express y z over z in a polynomial fraction. And then you're going to create partial fraction of y z over z. And again, remember, if I ask you to show me work, complete work, that means you have to show me the work for partial fraction, as how do you create partial fraction. So I'm not asking you to use residue function in MATLAB and just copy that and say that, hey, this is the work of partial fraction. No, I'm asking you that how you're going to calculate a, b, and c, multiply both sides by z minus 1, evaluate at z is equal to 1 to get a. All you have to do is to just explain like I'm explaining. If you have a factor a over z minus 1, multiply both sides by z minus 1, evaluate at z is equal to 1 to get a. That's it. And then you can do multiplication or evaluation in calculator or MATLAB. You don't have to show me multiplication or division of numbers. I mean, I'm not going to ask you to do that, but just I want to see that you know, if MATLAB is not available to you, let's say, then you at least know how to create partial fraction from a fractional polynomial. So of course you did that in the last chapter, and then you multiply both sides by z to get rid of this z here, and your equation will be just in terms of y of z. And then you're going to take the inverse z transform using the table, of course, table 5-1 in the book, inverse z transform to get y of n. So that's our standard method to determine the system response. Remember, system response means system response which can be impulse response or step response, or in general any system response. That means you have to express that y of n. So don't leave it as y of z and assume that it is system response. No, system response means that you are giving response in the time domain and you have to represent y of n. And it is not a difference equation. It is not a difference equation. It is a closed form solution that you can plug in any value of n and you can determine what is the value of y at that instant, that is at that value of n. So that's basically your system response from transfer function. It's an example from the book. I just copied and pasted. H of z is given as z plus 1 over z minus 0.5, and they're asking you to calculate impulse response, step response, and if xn is 0.25 to the power n, un then system response. So as you know, I mentioned, multiply x of z by h of z. In the first case, x of z will simply be 1 when x of n is an impulse. So you are going to multiply Basically, then y sub z will simply be h of z, and then you're gonna divide both sides by z. So y sub z over z. In this case, they're just taking h of z. Y sub z over z is equal to z plus 1 over z minus 0.5, a over z, b over z minus 5 as a partial fraction. You calculate a and b, multiply both sides by z and evaluate at z is equal to 0. So a is equal to -2, and to get b, multiply both sides by z minus 0.5 and evaluate at the root, which is z is equal to 0.5, and you're gonna get b is equal to 3. So you go ahead and plug that values of a and b, and then multiply both sides by z to get rid of this z that you introduced on the left hand side. So you're gonna get -2 plus 3z over z minus 0.5, and -2 is basically inverse z transform of -2 delta n impulse response, and this is simply 0.5 to the power n un, and that's what you see over here actually. The next is if xn is step function. So again, xz will be z over z minus 1, and you do the same thing. I don't want to go over it. And the third one, of course, is if x is 0.25, so xz will be z over z minus 0.25, and then you're going to introduce that h of z, x of z, and again write down, create the partial fractions, and then do the inverse z transform. Now you can plot these things. Remember, you plotted y sub n or x of n earlier. I forgot if you plotted or not, but in convolution you did actually. So the same way you can plot this. This is basically your equation. In n domain, you can take the value of n, 0 to whatever 100, and then you can plot this from n is equal to 0 to 100 and use the stem plot, so you will see how it is changing. Okay, in the next one we're going to discuss pole zero plot and system stability.